Okay, this is 2004 AP Physics B, Form B for response problem. It's number 2 for 2004, but it is the fourth one in your packet. In this problem, we have an experimental diving bell shown above, lowered from rest at the ocean's surface and reaches a maximum depth here, X max is 80 meters. Initially, it accelerates downward at a rate of 0.1 meters per second squared until it reaches a speed of 2 meters per second. Which then remains constant. During the descent, the pressure inside the bell remains constant at 1 atmosphere. The top of the bell has a cross-sectional area of 9 meters squared, and they give us the density of seawater as 1025. We'll come back to those two later. So first thing we need to do, calculate the total time it takes the bell to reach a maximum depth of 80 meters. So this is one of those problems where we have two parts to figuring out the time, right? So we're accelerating for the first part of the trip. So if I make a velocity time graph, right, we accelerate for some amount of time, right, until we reach a velocity here of 2 meters per second. And then from then on, we continue at constant velocity. So if we were graphing that, that's what it would look like. Okay, so what we want to do first is figure out what time, right, over which time are we accelerating? That's probably the best way to say it. Over what time are we accelerating? And we can do that because we have acceleration V naught and V. So the first thing we can do is just V equals V naught plus AT, right? And V naught is 0. So we get T equals V over A. And V is 2 meters per second over 0.1 meter per second squared, right? Which gives us 20 seconds. Okay, so what that means is that for the first 20 seconds of our trip, right, we're accelerating here as the dive bell goes down, right? But then at 20 seconds, we reach this velocity of 2 meters per second, and then it continues, right, at the constant velocity. So what we really need to figure out next is what depth this is happening at. We know it's probably going to happen at some depth less than 80 meters. Okay, so we can use our second kinematics equation here. X equals X naught plus V naught T plus 1/2 AT squared. Right, no initial velocity. We're looking for our height or our depth or our distance. So we have X equals 1/2 AT squared. Right, so this is just X equals 1/2 of 0.1 times 20 squared. Right, so we do that little calculation here and we get 20 meters. Okay, so what this says is that our total distance here, right, is 80 meters. For the first 20 meters, we're accelerating, right? But then of course, 80 meters minus 20 meters is 60 meters, right? So for the next 60 meters, we're moving at constant velocity, right? So this is the total depth, right? The depth that we're accelerating, and then this is the depth that we're moving at constant velocity. So we have the time for the accelerating part, so now we need to figure out the time for the constant velocity part, which again, easy. We're still gonna use, right, our second kinematics equation, X equals X naught plus V naught T plus 1/2 AT squared, right? But again, this is the constant velocity part of our trip, so we're not accelerating. Right, I can just make my X naught 0 and set X to 60 meters here. And so time equals X over V, right? So this is 60 over 2, right? Here's our V, that's the constant velocity, 2 meters per second. So our time here is 30 seconds. So what that tells us is that we spend the first 20 seconds of the trip accelerating downward, right, until we reach our maximum velocity. And then the remaining 30 seconds of our trip, we travel at a constant velocity. So our time total is just 20 plus 30 seconds, right? So T equals 50 seconds. All right, so that was our part A problem. I don't think I put an A up there. I'll write it there in case anybody really wants to see that. All right, so now we'll move along here to part B. Okay, part B says, shift that over for everybody a little bit. calculate the weight of the water on the top of the bell when it is at the maximum depth. Okay, so I kind of peeked ahead, right? And part C says calculate the absolute pressure on the top of the bell. So we're going to need the pressure. So I'm going to do this like in 2 steps, only because I know we're going to need pressure. Okay, so the weight of the water, we're really looking for here for part B, mg, right, of the water, right, because that's the weight of the water, right? So we're really here looking for the force of the water, right? So we know that pressure equals force over area, right? And so if I move this around, we get force equals pressure times area. Okay, so what we'll need to do first is figure out the pressure. So I'm just going to say pressure equals rho GH, right? So the density, now remember this, they told us it was seawater, not fresh water, so this was 1025, G 9.8. The height is the maximum depth there at the bottom, so that was 80 meters. And so when we calculate that all out, we get the pressure equals, where's my number here? 820,000 pascals. All right, and so that's just the pressure, but force is pressure times the area, right? And did they tell us the whole area? Oh yeah, they told us the top of the dipole. They gave us the area, right? So force is PA, right, which is just 820,000, right, times 9 meters squared, right? So the force equals, I switched over here to scientific notation, 7.38 times 10 to the 6th newtons, right? So just want to point out here, this, right, is our area at the top of the dipole that the water's pushing down on. Okay, so that was part B. Part C asks us calculate the absolute pressure on the top of the dive bell at the maximum depth, right? So this is why I bothered to calculate this all out here for the pressure due to the water, right? So here for part C, right, the absolute pressure equals the gauge pressure plus the atmospheric ATM, the atmospheric pressure. So we know the gauge pressure, right? This really is what we call the gauge pressure, right? So here P absolute equals 20000 plus in atmospheres, I'll just write it as 101. Right, because that's just kind of writing it out. I've been writing things out here. So P absolute equals, what do we get? 921 pascals, or 9.21 times 10 to the 5th pascals. All right, so moving along to part D. We have to calculate the minimum force necessary to lift open the hatch of the bell at maximum depth. All right, so we're back to doing a force calculation, and we know the pressure of the water, so we can just say, again, for part D, right, force is what we're looking for, but we know the pressure, so we can say pressure is force over area, right? So the force is the pressure times the area. Okay, so it's still, well, I'll come back to that. I do want to mention, right, that the area that we're talking about for this part of the problem here is the area of the hatch, right? So we've got all this pressure of the water, like all the way down, right, pushing down on the hatch, and now we're trying to push this hatch open, and they tell us the radius of the hatch, right? So of course we can get the area, right? We know that area here equals pi r squared. Okay, now the other thing to keep in mind is that we do have 2 pressures that we calculated, right? We calculated the gauge pressure and we calculated the absolute pressure. But since the dive bell is pressurized on the inside at 1 atmosphere, right, the difference between the pressure that is inside the bell and the absolute pressure is actually just the gauge pressure. Okay, so the amount of force that we have to, excuse me, push up with, right? Since we're already pressurized inside the bell at 1 atmosphere, we only have to push up with the amount of force due to the pressure of the water. So I'm going to say the force equals, this is the pressure of the water, which was, actually let me write this out as a nice equation. We'll say force equals pressure times pi r squared, right? So force equals the pressure from just the water, and then times pi times, the radius was 0.25 squared, right? So the force that we calculate here is 1.6 times 10 to the 6th newtons. All right, and last but not least here, part E says, what could you do to reduce the force necessary to open the hatch at this depth, right? So let's just write this as E, right? We want to force equals pressure times area, we just said. We want to reduce the force, right? So in order to reduce the force, right, we could reduce the area. Okay, that's easy. So 1, make the hatch smaller. All right, that's fine. Okay, now the second thing here is with the pressure. This one's a little bit less intuitive, right? We can't really change the pressure due to the water, right? Because we have a certain height of water above us. However, what we can change is we can change how the inside of the hatch is pressurized. So if we add more pressure inside, right, the diving bell, then it's going to push up and out on the hatch a little bit more, meaning that we need less force here. So our second thing that we can do, right, is pressure increase. Let's write is increase the pressure inside the dive bell. Yeah, I'll just leave it at that. Increase the pressure inside the dive bell, which will reduce the force that we need to push up and out.